Okay, so welcome back to this next video in which we are discussing how to measure the concentration of calcium within the cytoplasm of cells using the Fluo-4 dye. Okay, so we've discussed now that we firstly load cells with Fluo-4 using the Fluo-4 acetoxymethyl ester, okay, which then goes into the cells, has its ester links cleaved, and then ends up trapped within the cells. Okay, then what we do is we stimulate the Fluo-4 molecules with blue light, and we get green light coming back again, and we get this basal level of fluorescence coming from our cell monolayer, which is the fluorescence which results from some of the Fluo-4 molecules being bound to calcium, because you do have 100 nanomolar calcium concentration in the cytoplasm usually, and also the ones which are not bound to calcium at 100 nanomolar, those will still have some fluorescent properties. So the sum of those two effects gives us this basal fluorescence level here, okay, which is produced by normal cytoplasmic concentration of calcium. Then what we do is we stimulate the cells with carbachol. This causes the release of calcium from the endoplasmic reticulum, so cytoplasmic calcium concentration goes up. Therefore, the fraction of Fluo-4 molecules within the cells that are going to have calcium bound to them is going to increase, and therefore, when those Fluo-4 molecules bind calcium, and they didn't have calcium bound before, okay, they are going to have increased fluorescence properties, and therefore we're going to see an increase in the fluorescence signal that we're getting. Okay, then what will happen is very quickly the cell will desensitize to the carbachol, so it will stop reacting to it. It will stop releasing calcium from the endoplasmic reticulum. Okay, and then what will happen is the calcium will gradually be pumped from the cytoplasm back into the endoplasmic reticulum. Hence, the calcium level will fall, so fluorescence will fall back to the basal fluorescence level, like so. Okay, right, so that's brilliant. We have seen the response now, but we would like to be able to turn this change in fluorescence level that we've got into a change in calcium concentration, so that we actually know how much calcium has been released from the endoplasmic reticulum in response to that stimulation with carbachol. Okay, so what we then need to do is find two values, the Fmin and the Fmax. Okay, so the way that we find Fmin is by adding to the well a solution containing Triton X100, which is a detergent which will lyse all of the cells. So it will burst them all open, and the cytoplasmic contents will be released into the fluid. Okay, which means all the Fluo-4 molecules have been released into the fluid. Then what we also have in that solution is Bapta, which is a calcium chelating agent. So I'll just write that down here. And all that means is that it binds to calcium, okay, very powerfully. So it's going to remove all of the free calcium from this fluid, which means that none of the Fluo-4 molecules are going to have calcium bound anymore, because there's no calcium in the free solution. Okay, which means all of those Fluo-4 molecules will have the really bad fluorescent properties. So when we continue to stimulate with blue light, we're going to get very little green light coming off. Okay, even lower than we have before when the Fluo-4 molecules were in the cytoplasm, because at least in the cytoplasm they had the 100 nanomolar calcium concentration, whereas now they have nothing. Okay, so this is the absolute minimum fluorescence that the number of Fluo-4 molecules that we have loaded into all of the cells on this monolayer here could actually produce, basically. Now what we want to find is the maximum possible fluorescence that all of the Fluo-4 molecules in all of the cells of this monolayer could produce. Okay, and to find that, we need to load all of the Fluo-4 molecules with calcium. So all of the Fluo-4 molecules need to have a calcium arm bound to them. To do that, all we do is put a massive, great concentration of calcium in, usually in the form of calcium chloride, which dissociates into the calcium cation and the two chloride anions, okay, in solution. So we put a massive great concentration of calcium in here. This saturates all of this silly bacter that we added before to find Fmin, okay, and more than that, it puts a huge free concentration of calcium which then saturates all the Fluo-4 molecules, so we see a very large rise in the fluorescence level as all of the Fluo-4 molecules bind to the calcium, and then we get this maintained extremely high fluorescence level, which is the Fmax value. Okay, so that's what we've done so far. So, how are we actually going to use this information to work out what the calcium concentration was at this peak here? Okay, we would like to know what the calcium concentration in the cytoplasm of the cell was at this peak. We'd also quite like to know what the calcium concentration was at the basal level, although I've already told you that we know that fact for cells. It's usually 100 nanomolar or there around. Okay, but if we had those two calcium values, we could then subtract one from the other to get the difference. Okay, so although we do know that the basal calcium level will be around 100 nanomolar, this is one of the techniques you could use to actually find that piece of information in the first place. Basically, what we want to be able to do is we want to be able to take a fluorescent signal that we were getting from this monolayer of cells and convert that into an intracellular calcium concentration. Okay, so for ages we were getting this basal fluorescence level here. Okay, we would like to be able to convert that into calcium concentration. We would like to know what intracellular calcium concentration were these Fluo-4 molecules exposed to in order to give us this basal level of fluorescence here. Okay, then we'd like to ask, at this peak here, what concentration of calcium in the cytoplasm were the Fluo-4 molecules exposed to then to give us that peak value of calcium concentration. Sorry, peak value of fluorescence. Okay, right. Well, basically, we are in between Fmax and Fmin always here, okay? Which means that not all of the Fluo-4 molecules had calcium bound to them. So at every single point along here, not all of the Fluo-4 molecules within these cells had calcium bound to them. If they had, our fluorescence signal would have been up here at Fmax. Okay, so basically, what was the case is that in all the cells, and we'll assume that all of the cells roughly have the same number of Fluo-4 molecules in them, and that the concentrations of calcium in all of the cells at each point of this curve is roughly the same, i.e. they all start off with the same cytoplasmic calcium concentration, and in response to the carb call, the calcium concentration rises by the same amount. That obviously is not going to be true, but on average it will be true. Okay, so in each cell then, what's going to be the case is that you're going to have lots of Fluo-4 molecules. Okay, so I'll draw these here. So here are some Fluo-4 molecules, and I'll colour the Fluo-4 molecules in green would probably be the most appropriate colour. Okay, right. And some of these Fluo-4 molecules will have calcium bound to them, and some of them will not have calcium bound to them. Okay, so let's draw a calcium ion bound. So at the basal level of calcium, okay, where we have around 100 nanomolar calcium in the cytoplasm, very few of the Fluo-4 molecules will actually have calcium bound to them. Whereas when we've released calcium from the ER, the fraction of Fluo-4 molecules that have calcium bound to them will increase, basically. So it will be very, very helpful for us to know the fraction of Fluo-4 molecules that are going to have calcium bound to them as a function of the intracellular calcium concentration. And the way that you do that is with an equation known as the occupancy equation. So firstly, I'm just going to write the occupancy equation out, and then I'm going to explain where it comes from. Okay, so I'll give you a little derivation of it. So the occupancy equation is utterly essential in pharmacology. It's really, really important in pharmacodynamics. Okay, basically, this tells us the fraction of Fluo-4 molecules within the cells which are going to have calcium bound. Now remember, we're assuming that the number of Fluo-4 molecules in each cell is roughly the same. Okay, we're also assuming that the calcium concentration in each cell is roughly the same at all points of this curve. Okay, so the fraction of Fluo-4 molecules that are going to have calcium bound to them is given by the calcium concentration, which is the calcium concentration inside the cell. So I'll put calcium concentration I, so that's the cytoplasmic calcium concentration, divided by the dissociation constant plus the intracellular calcium concentration. Now note, this does not tell you the absolute number of Fluo-4 molecules that will have calcium bound to them. It tells you of the Fluo-4 molecules that are within a cell, what fraction of them will have calcium bound to them if this is the intracellular concentration of calcium. Okay, so the important thing that we then need to know is what this is. Okay, well, this is known as the dissociation constant. Okay, and this is specific for the interaction between Fluo-4 and calcium, basically. Okay, this in a way tells you how unstable the interaction between calcium and Fluo-4 is. It tells you about how much it wants to break apart over as compared to how much it wants to form, basically. Okay, it's 1 over the affinity constant, and I'll show you where that comes from in a moment. Now, dissociation constant has actually a really nice interpretation, which is that it is the concentration, okay, the concentration of calcium that you need to get half occupancy. Concentration for half occupancy. Okay, so what do I mean by that? I mean that if you let the intracellular calcium concentration equal the dissociation constant, so this is just a number, okay, and I'll give you the actual number that this is for Fluo-4 calcium interaction. So for Fluo-4 calcium interaction, it is 345 nanomolar, okay, so it's got the same units as concentration, basically. Now, you can obviously change the units here. You could change it to molar, you could change it to micromolar, millimolar, whatever you like. You need to make sure that the units that you are using for this dissociation constant are the same as the units that you are going to use for the calcium concentrations in here. What do I mean by that? I mean that if you're going to put in a calcium concentration in nanomolar, which would be a good idea because those are the sort of levels of calcium that you're going to have in the cytoplasm of cells physiologically, okay, then the dissociation constant also needs to be in nanomolar. So if these calcium concentrations are going to be quoted in nanomolar concentrations, then you need the dissociation constant also to be in nanomolar. If you're going to, for some reason, put these in molar concentrations, then you'd want your Kd in molar as well, so you'd have to times this number by 10 to the negative 9 to get it in molars. Okay, right. So, why then is this dissociation constant equal to the concentration which will give you half occupancy? Well, let's just imagine that the intracellular calcium concentration was 345 nanomolar. Okay, so we're imagining that the calcium concentration inside the cells is actually just equal to this number, which the dissociation constant actually is. Then if we plug that number into this formula, we will get 345 over 345 plus 345. So we put in the calcium concentration here is 345 nanomolar. We put in this calcium concentration here as 345 nanomolar, and then I've substituted the Kd in as 345 nanomolar. Okay, so that overall gives this formula. Okay, if you now work out what that is, that reduces down to a half. Okay, so that is telling you that the fraction of Fluo-4 molecules that will have calcium bound to them is a half. So if I draw a picture for this, we'll have a huge number of Fluo-4 molecules, and half of them will have calcium bound to them, and half will not have calcium bound to them. Okay, so here are the Fluo-4 molecules in green, okay, and we can see that half of them have calcium bound and half do not have calcium bound. Okay, so that's a nice literal interpretation of what this dissociation constant means. Okay, it is the concentration of calcium ions that you would need in order for the occupancy of Fluo-4 molecules to be half. Okay, so our basal calcium level was around 100 nanomolar, much lower than 340 nanomolar. So that tells us that at the normal cytoplasmic concentration of calcium, you've got far fewer than a half of the Fluo-4 molecules with calcium bound to them. Okay, right. So what I would now like to tell you about is how you actually derive this equation. Okay, so to do this, I'm just going to create a few little bits of nomenclature. Okay, so we will use N total to mean the total number of Fluo-4 molecules within one cell. Okay, so this is the number of Fluo-4 molecules in one cell. We're not going to know that, and we don't need to know that. But just for the derivation, it's helpful to think in terms of this. So number of Fluo-4 molecules within one cell. Okay, within one cell. So what basically we are going to do is, because we are assuming that each cell has the same number of Fluo-4 molecules within it, so we're assuming roughly that N total is the same for any cell in this monolayer within the well, okay? We're also assuming that the calcium concentration in the cytoplasm is going to be the same between all the cells, and therefore the occupancy of Fluo-4 molecules in each of those cells is going to be the same, okay? So we can just work out the occupancy in one cell, and then we'll say that that's going to be the same in all of the cells, basically. And then we've got the occupancy of Fluo-4 molecules within our well, basically, because we're assuming all the Fluo-4 molecules are inside the cells. Okay, right. So we're going to let N total be the number of Fluo-4 molecules within one cell. We're then going to let N... Oh, and by the way, this means all of the Fluo-4 molecules. It doesn't just mean 3 Fluo-4 molecules, it means Fluo-4 molecules that have calcium bound to them, as well as Fluo-4 molecules without calcium bound to them. So in this picture here, if we're imagining that that is a cell, a strangely shaped cell, but this is a cell, then we'd say that the N total was 3. We've got 3 Fluo-4 molecules in the cytoplasm of the cell. Okay, we wouldn't say it was just 1. It's not just the number of Fluo-4 molecules that don't have calcium bound to them. Okay, so NCA2+ now is going to mean the number of Fluo-4 molecules with calcium bound. So number with calcium. Okay, so in this picture here, what is the number with calcium? Well, we've got 2 that have calcium bound to them, so the answer here will be 2. Okay, those aren't going to be particularly important things, they're just going to be helpful for our derivation of this. Okay, you could derive this without those, but they're going to help us, basically. They're going to be very helpful in understanding this. Okay, so basically the idea is that there is a dynamic equilibrium. Okay, it's an equilibrium reaction, a reversible reaction. So basically, calcium can combine with Fluo-4, okay, to form a calcium Fluo-4 complex, which I'll just abbreviate as CF. And then the calcium Fluo-4 complexes can then break apart and return back to being calcium and Fluo-4. Okay, so you have lots of calcium ions in the cytoplasm of the cell, and then you have your Fluo-4 molecules in the cytoplasm of the cell. Okay, so just to explain the concept of a dynamic equilibrium then, okay, this is the concept. Basically, if you imagine starting this, imagine that you are God, and you have, you can press the button where time starts, okay, and before you press the button, time has not started, and you're just making an arrangement, and you're about to press the button for time to start. Okay, so if you imagine that initially, within a cell, you have put in lots of Fluo-4 molecules, so we'll have our 3 Fluo-4 molecules here. Okay, so time hasn't begun yet, you've just put the Fluo-4 molecules in here, and then you've put calcium ions in here as well. But at the moment, none of the calcium ions are bound to the Fluo-4 molecules. Okay, so here in orange are the calcium ions, and here in green are the Fluo-4 molecules. Okay, so what's going to happen basically is when you press go, when you press begin time, what's going to happen is some of these calcium ions are going to bang into Fluo-4 molecules and just happen to bind to them. Okay, so let's say this one will bang into this one and form a little calcium Fluo-4 complex. So what they'll form is something like this, where you've got calcium bound to Fluo-4. Okay, and this will continue on. More calcium ions will bind to Fluo-4 molecules, and you'll gradually get a higher and higher concentration of calcium Fluo-4 complexes. However, the calcium Fluo-4 complexes aren't hugely stable. If they were fantastically stable, then they'd remain bound now, but they're not brilliantly stable. So what instead can happen is they'll be dissociating as well. They'll sometimes fall apart. Okay, so what will gradually happen is initially, when you press go, the concentration of calcium Fluo-4 complexes in the cytoplasm will go up, okay, because you're now just forming the calcium Fluo-4 complexes. However, as the number of calcium Fluo-4 complexes rises within the cell, you'll start to get the dissociation of them as well. You'll start to get calcium Fluo-4 complexes breaking apart as well. And eventually it will reach a dynamic equilibrium. And what is meant by that? Well, the dynamic equilibrium is where the rate at which the calcium Fluo-4 complexes are made is equal to the rate at which the calcium Fluo-4 complexes are being destroyed. Okay, so here, in this picture, we have two calcium Fluo-4 complexes. Let's say that in a second, one calcium Fluo-4 complex will break down into a calcium and Fluo-4 molecule. Okay, so let's say of these two, one of them in a second will dissociate. So this one's going to break down into a calcium and a Fluo-4. But at the same time, from the free calciums and free Fluo-4 molecules, one of them, you'll get one calcium associating with a Fluo-4. Okay, then from 1 second to the next, the concentration of calcium Fluo-4 complexes is not going to change because you've destroyed one, but then you've remade one. So then you reach a point where the number of calcium Fluo-4 complexes doesn't actually change, even though you're continuously breaking them down and reforming them. The two actions cancel each other out so that you don't overall get a change in the concentration of calcium Fluo-4 complexes. Okay, that is the concept of a dynamic equilibrium. It's called an equilibrium because the concentrations of free calcium, free Fluo-4, and calcium Fluo-4 complexes are no longer changing. However, it's called dynamic because if you had a really powerful microscope and you could actually look at these molecules, you'd continually be getting calcium Fluo-4 complexes breaking apart and calcium and Fluo-4 molecules that are free binding together. So there's a lot happening even though nothing is actually changing, basically, and that's why it's known as dynamic equilibrium. Okay, so basically the idea here is that within each of these cells you have reached this dynamic equilibrium where you have a fixed concentration of calcium Fluo-4 complexes and a fixed free concentration of Fluo-4 and a fixed free concentration of calcium. Now, that's where these numbers come in now. N total, remember, is the total number of Fluo-4 molecules in the cell, so it's 3 here. N calcium is the number with calcium bound, so in this case it's 2. Okay, if we wanted to know how many were actually free, i.e. they don't have calcium bound, the number that don't have calcium bound would be the N total take away the NCa2+. Okay, this would give us the number that don't have calcium bound. In this case 1, which is just 3 minus the number that do, which is 2. Okay, so 1. Okay, now, as part of the derivation of the occupancy equation, you assume that the number of calcium ions within the cell is much, much, much bigger than the number of Fluo-4 molecules that have bound calcium. Okay, so what do I mean by that? I mean that in a real cell, you might have, a few million, let's say, Fluo-4 molecules with calcium ions bound to them, whereas the number of calcium ions that you will actually have in that cell will be gazillions, basically. Huge numbers. Even though it's only 100 nanomolar, that's still huge, because you have to remember that a mole is 6.022 times 10 to the 23 calcium ions. So there's a huge number of calcium ions. So you assume, basically, that the calcium concentration in the cytoplasm does not change because calcium has bound to the Fluo-4 molecules. Okay, of course it actually does. The free calcium concentration does go down because the calcium ions are binding to the Fluo-4 molecules, but we're going to assume it doesn't. So what do I mean by that? Well, if we go back to this picture here, we started off with all the calcium ions free. Okay, once we've reached the dynamic equilibrium, some of the calcium ions will be bound to the Fluo-4 molecules. So the free calcium concentration has gone down. We are going to assume that it goes down by such a tiny amount that we don't even need to bother acknowledging that it goes down, okay? And that's true, okay? Because the number of Fluo-4 molecules that are actually bound to calcium, so the number of these calcium Fluo-4 complexes, is tiny compared to the number of calcium ions in the cytoplasm. I know I've not shown that in this picture. I've shown 4 calcium ions and 2 Fluo-4 complexes with calcium ions, okay? But in reality, the calcium concentration dwarfs the Fluo-4 concentration. So you don't need to worry about changes in the calcium concentration due to calcium ions binding to Fluo-4 molecules. Okay, right. So we can work out the concentration of calcium Fluo-4 complexes using the fact that this is going to obey an equilibrium equation. Okay, so I'm just going to go over onto the other page. Right, so at the moment we've got this relation where calcium ions can combine with Fluo-4 molecules to create calcium Fluo-4 complexes, and then those are going to dissociate back again. So we now have to ask, what we want to know is what concentration of calcium Fluo-4 complexes are we going to have at this equilibrium? Now, how can we work that out? Well, what we know is that the rate of the forward reaction is equal to the rate of the backward reaction at equilibrium. Okay, and that's what we're going to use. So we're going to use something known as the law of mass action. Okay, now, the law of mass action says that the rate of a reaction, okay, so this is the law of mass action, that the rate of a chemical reaction, is proportional to the product of the concentrations of the reactants, okay, is proportional, so that's the symbol for is proportional, to the product, so multiply them all together, product of concentrations of reactants. Okay, so if we want the rate of the forward reaction, then the rate of the forward reaction is going to be some constant because it's proportional. So this is just the constant of proportionality. So I'll put an arrow here for the rate of the forward reaction. Okay, it's going to be, let's put k plus 1, okay, which is the rate constant for the forward reaction. So it's just some number. Okay, we don't know it, but it doesn't matter that we don't know it. Okay, and then it's going to be times the calcium concentration at dynamic equilibrium. In principle, this should be the calcium concentration once you've reached dynamic equilibrium, but I've just argued that we don't need to distinguish between the calcium concentration at dynamic equilibrium and the calcium concentration before dynamic equilibrium had been reached, because it's not going to change that much at all. Okay, so we'll just call this the calcium concentration within a normal cell. Okay, right. Then it's times the number of Fluo-4 molecules that are actually free in the cytoplasm of the cell at dynamic equilibrium. Okay, so what is the concentration of those in the cell at dynamic equilibrium? Well, the actual absolute number that are free is going to be the total number, okay, subtract the number that are bound to calcium. Okay, remember I showed you that here. If we want to know the number that are free, then it will be the total number within the cell, subtract the ones that are involved in calcium Fluo-4 complexes. And then we'll just have to divide by the volume of the cell, okay, to turn that into a concentration. Okay, so that's the rate of the forward reaction. Now if we want the rate of the backward reaction, it will again be some rate constant, the rate constant of the negative reaction, and now it's times the concentration of calcium Fluo-4 complexes. Well, we know the absolute number of calcium Fluo-4 complexes, that is NCA2+, okay, that's just that we defined that number to be the number of Fluo-4 molecules bound to calcium, okay, and then we can divide that by the volume to turn it into a concentration. Okay, so we will now say that at dynamic equilibrium, the rate of the forward reaction has to equal the rate of the backward reaction, okay? Because that's the definition of dynamic equilibrium, because that's the condition that you need in order for the concentrations of things on both sides to not change, basically. If you're at this equilibrium where calcium concentration, Fluo-4 concentration, and calcium Fluo-4 complex concentration are not changing, then that must be because the rate of this forward reaction is equal to the rate of the backward reaction. Okay, so we can put these two equal to one another. So that's going to give us this equation, K plus 1 times the calcium concentration, and I'll now put calcium concentration here, and we'll put intracellularly there. Okay, now we'll have this here, N total minus NCA2+, okay, over V is going to be equal to K negative 1, and then we'll have NCA2+ over V. Now, if we wanted, we could work out from this the concentration of calcium Fluo-4 complexes here. We could isolate this on its own, and we get it in terms of the total concentration of Fluo-4 molecules within the cell, which is something that we don't know. Instead, what we're going to work out is the occupancy, because remember, that's what we were trying to derive. We wanted to derive the occupancy equation, which tells us at dynamic equilibrium what fraction of Fluo-4 molecules are actually bound to calcium. So we can't work out the actual number that are bound to calcium, not without knowing the actual number that were in a cell to start with, which is something that we don't know. Okay, instead, what we'll work out is the fraction of Fluo-4 molecules within that cell that are bound to calcium. Okay, and that's something that you don't need to know the actual number that you put in initially to work out. Okay, so what is the fraction in terms of these numbers? Well, it's just going to be NCA2+, which is the number which are bound to calcium, over the total number in the cell, which is N total, like so. So this is the occupancy. So what we're now going to do is rearrange this equation to try and work out occupancy then. Okay, so the first thing that we can do is we can cancel the V on either side. Okay, so we're going to get rid of the V on either side. Then we're going to multiply out this brackets here. Okay, so what's that going to do for us? Well, we've got K plus 1 now, times the concentration of calcium intracellularly, okay, and then we've got times N total, okay, and then we'll have minus K plus 1 times the calcium concentration intracellularly times NCA2+. Okay, so that's just that bracket multiplied out, okay, just using distributivity. And then that's going to equal K negative 1, the rate constant of the backward reaction, times, whoops, not like that, times the total number of Fluo-4 molecules that have calcium bound to them, like so. Okay, I'm then going to move this portion here onto the other side so that I'm going to get all of the NCA2+ terms on one side. Okay, so what that is going to yield is, if we write out this side first, so we'll have K plus 1 here, okay, times the intracellular calcium concentration here, times the total number of Fluo-4 molecules within a cell, okay, is going to equal, now I'm going to factor out NCA2+. So I'll get NCA2+ times, then we've got the negative rate constant here, and now I've brought this portion, which I'll underline in purple here, I'm bringing this portion over to the other side. I'm factoring this out. When I bring this over to the other side, it's going to become a positive, so we're going to have plus K plus 1 times the intracellular calcium concentration here. Okay, right. So this portion here has come from here, okay, or rather this portion here has come from here, and this bit here has come from that purple bit here, okay, and this portion here has come from this portion here. Okay, right. Now what I can do is I can just divide through by n total on this side here, and then I can divide through by this thing here. So basically what I'm trying to do is I'm trying to get NCA2+ over n total, which is my alpha here. So what I'm going to do is I'm going to divide both sides by n total. Okay, that will cancel it from this side, and then I'll have it underneath NCA2+ here. So I'm going to effectively move that down here. And then I'm also going to move this portion onto this side by dividing both sides. Okay, so this portion is going to go down here. So what I'm then going to get is I'm going to get NCA2+. So I'm now swapping it round, okay, so that I've got it in the more normal formula style. Okay, so this is this side here, NCA2+ with the n total over it. Okay, and this is obviously what we've defined to be equal to alpha, is equal to this portion here, which is K plus 1 times the intracellular calcium concentration, okay, divided by K negative 1 plus K plus 1 times intracellular calcium concentration. Okay, so that then is this portion here that has been brought down underneath this portion, and that now gives us the fraction of Fluo-4 molecules that at dynamic equilibrium are going to have calcium bound. Now we're very close to that occupancy equation that I wrote down initially. Okay, all we now need to do is divide top and bottom in this fraction by K plus 1. So if we divide the top by K plus 1, then we just get calcium concentration intracellularly here. Okay, if we divide the bottom by K plus 1, we get K negative 1 over K plus 1 plus, and then the K plus 1 has gone from here, so we'll then get calcium concentration intracellularly. Okay, now this is what we define to be equal to the dissociation constant. It's the backward rate constant over the forward rate constant. So that's why it's called the dissociation constant. It kind of gives how much the calcium Fluo-4 complexes want to break apart as a ratio compared to how much they want to form together, basically. Okay, so that's the dissociation constant, and then we've got our occupancy equation that I wrote down initially. Okay, so to summarize then, that was a derivation of this equation that is going to be extremely important. We can't do anything without this equation now. You will see in the next video how important this is going to be. But to summarize, what this is telling us is you give me an intracellular calcium concentration within the cells. I have this constant. This is a known constant. You can look this up on the internet for the interaction between Fluo-4 and calcium. This was worked out long ago. Okay, this is 345 nanomolar. Okay, I can stick that intracellular calcium concentration into this formula, and it will give me the fraction of Fluo-4 molecules within the cell that will have calcium bound to them. Okay, and that doesn't, we don't care how many Fluo-4 molecules have actually been loaded into the cell. If you've loaded 10 in, this formula will work. If you've loaded in 1,000,000, this formula will work. This gives you the fraction of whatever total number you've added in that will have calcium bound under this intracellular calcium concentration. The assumption is that the number that you have loaded in is nowhere close to the actual number of calcium ions within the cell. Okay, if the number of Fluo-4 molecules that you loaded into the cells actually got close to the number of calcium ions that are within the cell, then this model would break. Okay, that was, remember, the assumption that we made in order to use this model. Okay, if the number of Fluo-4 molecules gets anywhere close to the number of calcium ions within the cells, then this no longer works, okay? But you will never ever load that sort of number of Fluo-4 molecules into the cell, okay? So always the number of Fluo-4 molecules will be tiny compared to the number of calcium ions, and this formula then holds true, okay? So I, for one, find that pretty incredible that this formula it doesn't matter how many Fluo-4 molecules you've actually loaded into the cell. Whatever number you've loaded, the fraction of them that will end up with calcium bound doesn't really vary that much unless you take the Fluo-4 concentration to extremes, which you never would. Okay, so this is going to be really, really important because this is going to tell us, for a certain calcium concentration, what fraction of the Fluo-4 molecules are going to be fluorescing at the increased fluorescence level, and what fraction, which will be the other 1 minus alpha, the rest of them, which are not fluorescing at that enhanced fluorescence and are fluorescing at the really weak fluorescence. Okay, and in the next video we will see how this all comes together now for us to be able to convert a fluorescent signal into an intracellular calcium concentration.